I thank you all for watching my videos all these years. Please like my videos and share them with your friends and colleagues. Please subscribe my channel if you have not already subscribed. Thank you. We now discuss the solution of a problem from the question paper CSIR National Eligibility Test held in the month of June 2023. This question is broadly from algebra, in particular from group theory, and it is related to surjective group homomorphism. This question is from the part C, which is a multiple select question. There can be more than one answer and it carries 4.75 marks. The question ID is 704085. This question is suitable for all these examinations. Right. The given question is, let G1 and G2 be two groups and phi, a map from G1 to G2, be a surjective homomorphism. Which of the following statements are true? We are given four options. Option 1, if G1 is cyclic, then G2 is cyclic. Option 2, if G1 is abelian, then G2 is abelian. Option 3, if H is a subgroup of G1, then phi of H is a subgroup of G2. Option 4, if N is a normal subgroup of G1, then phi of N is a normal subgroup of G2. The options are looking very straight and almost known to us. Right. Let's now discuss the solution of the problem in detail. We have two groups, G1 and G2, and phi, a map from G1 to G2, is a surjective homomorphism. Surjective homomorphism. So we require this. That is, what do you mean by surjective homomorphism? It is a onto homomorphism. That is, phi from G1 to G2 is a homomorphism and phi of G1 is the whole of the codomain. That is G2. Let's take the option 1. If G1 is cyclic, then G2 is cyclic. Is it true? Let's see. We have G1 is a cyclic group, let us say. It is generated by A. That is, G1 is a cyclic group generated by A. That is, A is a generator of G1. Let X be any element in G2. Let us take X is any element in G2. So, since phi is a surjective homomorph, it has a pre-image. That is, there exists a B belongs to G1 such that phi of B is equal to X. Right. So, since G1 is a cyclic generated by A and B belongs to G1, B is equal to A power K for some K belongs to Z. Yes, because G1 is a cyclic. Right. So now X is equal to, what is X? Phi of B. That is equal to phi of, what is B? A power K. So apply homomorphism. Phi of A multiplied by a k times is equal to phi of a multiplied by phi of a multiplied by phi of a k times. That is phi of a whole to the power of k, because phi is a homomorphism. Thus, every element of G2 is generated by phi of a, because x is taken as any element of G2. Now we have obtained x is a power of k. So phi of a whole to the power of k. So thus every element element of G2 is generated by phi of a. That is, G2 is generated by phi of a. Right, cyclic group. So thus G2 is cyclic. So thus we have proved when G1 is cyclic, then G2 is also cyclic. In this, we have used the fact that phi is a surjective homomorphism is necessary here. Right. So thus option 1 is true. Let's move to the next slide for the discussion of option 2. Option 2. If G1 is abelian, then G2 is abelian. Is it so? We have G1 is an abelian group. That's the hypothesis. We want to prove that G2 is also an abelian group. So for that, you take any two arbitrarily chosen elements of G2 and show that they commute. Thus every pair of elements in G2 will commute, and thereby G2 will be abelian. So for that, let x and y be any two elements of G2. Since phi is surjective, there exists, its their pre-images for x and y. So since phi is surjective, there exists elements a, b belongs to G1 such that phi of a is x and phi of b is y. Agreed? Now xy, the product, is equal to phi of a, phi of b, right? Because phi is homomorphism, it is phi of ab, right? Now where are these ab? AB are coming from G1. What is G1? G1 is abelian. Therefore, for AB is equal to BA because G1 is abelian. So this is equal to phi of BA because AB is equal to BA since G1 is abelian. Now phi is homomorphism. Therefore, phi of BA is equal to phi of B, phi of A because phi is homomorphism. Phi of B is Y, phi of A is X. So thus, we have proved xy is equal to yx. How x and y are taken? For any two elements. Therefore, every pair of elements commute in G2. Thus, xy is equal to yx for all xy belongs to G2. That will show you that G2 is abelian. In this also, you have used the fact that phi is surjective. Right. So, when G1 is abelian, G2 is also abelian. Right. Thus, option 2 is true. Move to the option 3 in the next slide. Option 3. If H is a subgroup of G1, then phi of H is a subgroup of G2. This is also true. We have H is a subgroup of G1. We want to prove phi of H, its image, under phi is a subgroup of G2. Note that phi of H, where the phi of H will be? In G2. It is a non-empty subset of G2. Obviously, because G1 is a group. So, H is a subgroup. Because H is a subgroup, phi of H will be a subset of G2 and it is non-empty. Very obvious. Right. Now, let us take any two elements x and y of phi of h. Right. Now, there exists x and y are in phi of h. There exist elements, pre-images, a, b belongs to h, such that phi of a is equal to x and phi of b is equal to y. We are not using that phi is a surjective homomorphism. We are taking two elements x and y in phi of h. There exists elements a, b belongs to h such that phi of a is equal to x and phi of b is equal to y. For this, we don't require surjectivity. Agreed. Now, how do I prove that phi of h is a subgroup of G2? We have taken two arbitrary elements, and it is sufficient that you prove that phi of h is closed under the operation. Why only that one condition? Normally, we require the inverse also. We don't. So, now xy inverse. Yeah, second condition is also necessary for us. Correct. So, xy inverse is equal to phi of a into phi of b whole inverse. Phi of b whole inverse. That is equal to phi of a into phi of b whole inverse is phi of b inverse, because it is a homomorphism. So, we are taking that two conditions, xy inverse clubbed in. So, phi of a into phi of b inverse is phi of a b inverse, because phi is homomorphism. So, now where are this a and b? A and b are in H. What is H? H is a subgroup. Therefore, AB inverse also belongs to H. For all AB belongs to H, since H is a subgroup of G1. So, phi of AB inverse, where AB inverse belongs to H, will imply phi of, this belongs to phi of H. So, thus xy inverse is equal to phi of AB inverse is equal belongs to phi of H. For all xy belongs to phi of H is a necessary and sufficient condition. Therefore, phi of H is a subgroup of G2. Thus, option 3 is true. Agreed. We move on to option 4. If n is a normal subgroup of G1, then phi of n, its image, is also a normal subgroup of G2. So, we are given n is a normal subgroup of G1. We wanted to prove its image under phi of n is also normal subgroup of G2. Right. We take any clearly, first of all, is phi of n a subgroup of G2? Yes. Since n is a subgroup of G1, we have already seen in option 3, phi of n is a subgroup of G2. Agreed. We wanted to now prove that it is phi of n is a normal subgroup of G2. For that, let x be any element of G2, right? And y be any element of phi of n. Then to prove phi of n is a normal subgroup of G2, the necessary and sufficient condition is x inverse belongs to phi of n. Right. Because there are any two elements, this is sufficient. If you prove, then it will be true for all xy. We claim this one. So, then, now x and y, x is any element of G2. X is any element of G2 means it has a pre-image because it is surjective. There exists a belongs to G1 such that phi of a is equal to x because phi is surjective. And y belongs to phi of n means there exists a n belongs to n such that phi of n is equal to y. We don't require that phi to be phi. See, we are not using surjectivity. We are taking an element of phi of n. Therefore, there is an element n belongs to n such that phi of n is equal to y. Now, x inverse is equal to phi of a into phi of n into phi of a whole inverse. And that is equal to phi of a into phi of n into phi of a whole inverse is phi of a inverse because phi is a homomorphism. Because phi is a homomorphism, they will go inside phi of A n A inverse. Agreed. Now, what is A? A is in G1. What is N? N is in N. What is capital N? Is a normal subgroup. Therefore, A n A inverse belongs to capital N. Right? Because N is a normal subgroup G1. So, therefore, this belongs to phi of capital N. So, thus xy inverse is equal to phi of A n A inverse. That belongs to phi of n, capital N, for all A belongs to, for all x belongs to G2. Here there is a print mistake. For all x belongs to G2 and y belongs to phi of n. Agreed? Agreed. So that means phi of n is a normal subgroup of G2. Thus, option 4 is also true. So, in this question, all the 4 options are coming out to be true. Therefore, the answer to this question is options 1, 2, 3 and 4. That is the detailed discussion of the solution of the problem from group theory, which is related to the surjective group homomorphism. This question is straightforward. Almost all of them we do, as examples under exercise. I am sure that you have done this in your examination. I am sure that you have understood the solution of this problem. Thank you for watching this video now. Please like and share my videos with your friends and colleagues and subscribe my channel if you have not already subscribed. We will meet once again for another discussion, in the next episode. Enjoy learning. I wish you all the best. Thank you.